Welcome to Online Precalculus. Tonight, we're going to cover section 4.4, trigonometric functions of any angle. The objectives for this function are to use the definition of trigonometric functions of any angle. We're going to use the signs, positive or negative, of the trigonometric functions in different quadrants to help evaluate these trig functions. We're going to use something called, or find something called reference angles, and then we're going to combine reference angles and knowing what quadrant we are in to evaluate trigonometric functions anywhere or for any type of angle. All right, so in the last section, we focused mostly on triangles, right? We used SOHCAHTOA. We talked about the 6 trig functions of acute angles shown right in these pictures right here. We'll come back to that in a second. Okay. Note that all these angles we're going to start are going to be, so think of these triangles, we're going to start them in standard position. Okay, so we're going to start these angles on the positive x-axis, and we're going to swing around in a positive direction towards the terminal side of theta. If we then drop an altitude, okay, if we draw a line down to the x-axis or up to the x-axis, we're going to make a right triangle. All right, and this right triangle is going to go from this coordinate xy to the origin and then straight down to the x-axis. Okay, sort of looks like something like this. So if we're in the first quadrant here, right, you can see that I have my triangle like that. Second quadrant, here's my triangle, goes from this point to the origin as my hypotenuse. Same thing, my right triangle and my right triangle. Okay, so with all these, depending on the quadrant that we're in, we have, right, every point, it's got an x coordinate, it's got a y coordinate. The way you get there is you go left or right and then up or down. So you have the two sides of the right triangle, and as long as this angle is in standard position, which means it starts on the positive x-axis and then opens in either direction, it doesn't matter, but it opens in some way spinning around the origin, right, wherever you stop, wherever this point is, you can make a right triangle out of it, which means that we can take the right triangle definitions of the trig functions and sort of combine them with the unit circle definition, because now we're not saying that the radius is equal to 1. We're not saying that this is on a circle. We're just finding an angle. Okay. So for all three of those, for all these things right here, right, for all those pictures, all these angles are in standard position, but they're not acute. The only angle that is acute is that one. Okay, that is obtuse. That is bigger than 180 degrees, and so is this one. Okay, so we can extend the definitions that we had for the 6 trigonometric functions to include angles as well as quadrantal angles. Okay, remember quadrantal angles are angles that stop on a quadrant line. So that's 90 degrees, 180, or pi over 2, pi, and 3 pi over 2, and 2 pi as well. So the point xy can be any point on the terminal side of the angle theta other than the origin, right? We're not gonna make an angle with we're not gonna find the trig function of an angle that has no radius. So if you think about this for a second, right? If I knew the x coordinate and the y coordinate, if I knew those two lengths, the way I could get the radius is from the Pythagorean theorem, right? Because x squared plus y squared is equal to r squared, or a squared plus b squared is equal to c squared. So by taking that Pythagorean theorem right there, we know the radius to be a distance from here to here. Distance formula, Pythagorean theorem, one or the other, comes right from each other. So as long as that is true, we can find the 6 trigonometric functions based on not necessarily SOHCAHTOA, kind of like that, because the y coordinate would be the opposite side and the r coordinate would be the hypotenuse. Okay, but we're going to put these in terms of this coordinate instead of having to draw a right triangle every time. So instead of having to say, okay, here's a triangle, right? If I want to find the, um, right, if I wanted to find the 6 trigonometric functions of this angle, I could look at this angle inside of the triangle and then use opposite side, the hypotenuse, and then I would have to manually decide whether or not this is in a different quadrant. So that gets a little more complicated to stick with the SOHCAHTOA idea. So we're going to shift that a little bit and just use the 3 points that we have on our circle, the x and y coordinate and the distance from 0, the radius that would form this circle if we made a circle. And in a unit circle, right, we said the sine was equal to y because r was 1. Okay, but now we're going to talk about how we can find trig functions of any angle on any sort of radius circle. So the sine would be y over r, cosine is x over r, tangent is y over x, and then my reciprocal relationships all still hold. Just flip them over. Okay, so let's find let P be -3, -5, and that is a point on the terminal side of theta, and we're going to find the 6 trigonometric functions of theta. And this is another reason why the triangle definition, SOHCAHTOA, doesn't really work in this case, because how do you have a triangle with a side that's -3 and -5, right? You could just say, okay, it's +3 and +5 and draw out the triangle like this, and then use SOHCAHTOA, but now we're changing a lot of signs and we're making a lot of changes there. So let's stick with the circular definition. So the sine of theta, the cosine of theta, and the tangent of theta. Well, I know x is -3. I know y is -5. I just need to find r. And the way that I find r is the square root of -3 squared plus -5 squared. So that's 9 and 25. So that's the square root of 34, which doesn't really simplify. So the sine is, y is negative. So it's -5 over the square root of 34. I think you know that we can't leave it like that. So it's -5 square root 34 over 34. If I multiply the top and the bottom by the square root of 34. Same thing for cosine, which is -3 over the radius, which is -3 square root of 34 over 34. And the tangent would be y over x, which would be -5 over -3, which turns positive. Okay? And then I would usually write them over here right next to it, but I ran out of room. So the cosecant, the secant, and the tangent, or sorry, the cotangent, are just reciprocal relationships. So you could flip this one over here, but then you're going to have to rationalize the denominator again, so just flip the original one. So that is negative the square root of 34 over 5. This would be the square root of 34 over 3, negative, and 3 over 5. Okay? So the point of this is that we can take the same ideas that we used with the unit circle. We can take the same ideas that we used in the last section with SOHCAHTOA, and now we can just extend that to a circular definition in order to use a coordinate and the radius to build out all my 6 trig ratios. Let's try this one. 6 and 8, find the sine. Okay, so in order to do that, we need to know the hypotenuse. Or you need to recognize that this is a Pythagorean triple. It's a 3, 4, 5 triangle multiplied by 2. So the radius would be 10. but let's just do that just to be sure. 6 squared plus 8 squared, which is the square root of 36 plus 64, which is 100, which is 10. So the sine would be the y-coordinate over the radius, which would be 4/5. Okay, so we're given a point on the terminal side of the angle, right? If we have a point on the terminal side, we can always find the different ratios, provided it's in standard position. Okay. So how do we find the values for trigonometric functions for a quadrantal angle? First, we draw the angle in standard position. Choose a point P on the angle's terminal side. Could be at a distance of 1, a unit circle, or it could be anything else. It doesn't really matter because it's a ratio. Remember that picture that the size of the triangle, right? The sine of these two angles was the same, right? No, even though these two triangles are different, the sine, the ratio at this angle and this angle is always going to be the same. So it doesn't matter what kind of radius you're choosing here, as long as you have the angle correct and it's in standard position. So trigonometric functions theta depend only on the size of theta and not the distance from the origin, just what I said. So why make it harder for yourself? Use 1. Makes it easier, okay? All right, so 0 degrees or 0 radians. Evaluate, if possible, the sine and the tangent function. Let's do all three. Let's do sine, cosine, and tangent. Because I think, yeah. So let's do sine of theta, cosine of theta, and tangent of theta. Okay, so 0 degrees. So if we have an angle of 0 degrees, that point is right there. Okay, if we assume that the radius is 1 here, that gives me a coordinate of 1, 0, a radius of 1, so that means x is 1, y is 0. Okay, sine is y over r, 0 over 1. Cosine is x over r. Tangent is y divided by x. So the sine is 0, the cosine is 1, and the tangent is 0 at 0 degrees, 0 radians. At 90 degrees, pi over 2 radians, the sine, cosine, and the tangent. Now where are we? Right there, right? This is an angle of 90 degrees, pi over 2 radians. This is a coordinate right here. I could use 1, right, just like the last one, but what I said before is you don't have to, right? Let's call this point 0, 2. So that means x is 0, y is 2, r is the square root of 2 squared plus 0 squared. That's the square root of 4 plus 0, which is still 4. So the radius is 2 as well. Makes sense. This distance is 2. Okay. So when you're dealing with quadrantal angles, the radius and either the x and y coordinate are going to be the same number, except the radius is always going to be positive. Okay. Sine is y over r. 2 over 2, which is 1. Cosine is x over r, 0. Here's a weird one, though. Tangent is y over x. So that's 2 over 0, which is undefined. Okay? So it is possible for the tangent to be undefined at different spots. Sine and cosine are never undefined. You always have an x and a y coordinate, but you don't always have a ratio. 180 degrees, that's here. Let's say that this distance is 1, make it easy. So that's -1, 0, with a radius of 1. This distance, right, distance from 0 is 1. So the sine is going to be the y coordinate over the radius. The cosine is going to be the x coordinate, -1, over +1, which is -1. And the tangent is going to be the y coordinate divided by the x coordinate. All right? And then finally, for my last quadrantal angle, 3 pi over 2, that is this angle right there, 3/4 of the way around the circle. The sine, cosine, and tangent at this angle, let's call that 0, -1, which makes the radius +1. Radius is always positive, right? The distance is always positive. Sine becomes -1, cosine is 0, tangent is, again, y divided by x, -1 divided by 0, which is undefined. Okay, so we can evaluate the trig functions of all the quadrantal angles. We can evaluate the trig functions if we know a specific coordinate, an x and a y coordinate. Okay, let's talk a little bit about the signs of trig functions. So we just learned, we just evaluated trigonometric functions of quadrantal angles. Let's go back to non-quadrantal angles, everything else. So if theta is not a quadrantal angle, okay, the sign of the trig function depends on the quadrant which theta lies. So in all 4 quadrants, the radius is positive. The distance from 0, right, no matter what, if I'm drawing an angle, right, and I'm starting it from standard position, starting it from the positive x-axis, this distance, no matter what it is, could be 1 for a unit circle, could be whatever, doesn't matter. Okay, whatever that distance is will be positive, right? Distance is always positive. The radius is always positive. However, here we're in the second quadrant, so that means x is going to be negative and y is going to be positive. Okay, if we were down here, x and y would both be negative, and if we were over here, the x would be positive and the y would be negative. So these ratios, right, the ratios for sine, cosine, and tangent and their reciprocal values are going to depend on what quadrant the point lies in. So if it's in quadrant 1, x is positive, y is positive, so that means all the functions are positive. In quadrant 2, x is negative, y is positive, so that means since the sine relies on y, the sine is positive, and the cosecant is reciprocal. In quadrant 3, x is negative, y is negative, that means the sine is negative, the cosine is negative, but the tangent, which is y divided by x, is going to be positive. And in the fourth quadrant, cosine is positive. And the way we like to remember this, since we go in this order right here, A, S, T, C. Okay? And we usually write that like A, S, T, C, which tells me that everything's positive here, the sine's positive in this one, tangent's positive in this one, and cosine is positive in that one. There's a couple tricks, little mnemonic devices to help you remember this. So a phrase that might be helpful would be a smart trig class. The one I like to remember is all students take calculus, which may or may not be true. But that's sort of the one that I remember using the most. Okay, so just a little mnemonic device to help you remember this, to help you remember what trig function is positive in what quadrant. Okay, so let's see what we would do with this. Tangent is negative, cosine is positive. What quadrant is theta in? So all students take calculus. Well, tangent is negative. Can't be there, can't be there. Cosine is positive. Can't be there, we're there. We are in quadrant 4. So the answer would be quadrant 4. All right. And you do it just like that, okay? So eliminate the you need two, right? Uh, you need two different trig functions, because if I only told you that the cosine was positive, you would have two choices, this one or this one. You need another thing to eliminate one of the other ones. Okay? So, what can we do with this? Given that the tangent is negative and the cosine is positive, right? Cosine is greater than 0. Find the cosine and the cosecant. Okay, so here's the thing, is the tangent there gives me y over x. So that's going to be 2 over 3. But one of them has to be negative. Not both, only one. Okay? And I know that the 2 is the negative and not the 3, because cosine represents the x coordinate, x over r. So I know that x is going to be a positive 3, y is going to be a negative 2. Now I need to find the radius, which I get by just doing negative 2 squared, or I should have done it the other way, but same thing. So that's 4 and 9 is 13. So this is the square root of 13, which makes the cosine equal to 3 over the square root of 13, which is 3 square root 13 over 13. Positive. Cosine is positive. Okay, cosecant. Cosecant, it is the reciprocal of sine. So it's 1 over the sine. Okay, so the sine would be negative 2 over the square root of 13. All right, and I'm just going to flip this to give me my cosecant, and that would be negative square root of 13 over 2. Okay, so tangent is negative, so that means I could be in this quadrant or this quadrant. With the cosine being positive, I now know I'm in the fourth quadrant, which means the x coordinate must be positive, the y coordinate must be negative, and that's how I know which one of these, the 2 or the 3, was the negative number, and it was the 2, because the y coordinate was negative, because I'm in the fourth quadrant. Okay? So, let's take this. I don't think I had another one. No. All right, let's take this a little bit further to something called reference angles. Okay. So we're often going to evaluate trig functions of positive angles greater than 90 degrees. Okay. But instead of always having to memorize the whole unit circle, which we should, and instead of extending that to all coterminal angles as we go spin around the circle more than once, right? There's an easier way to do it, okay? And the way we're going to do it is we're going to use a positive acute angle. The positive acute angle is called a reference angle. And what a reference angle is let theta be a non-acute angle in standard position that lies in any quadrant. Take this angle. Here's theta. Okay? It is a non-acute, it's greater than 90, standard position, and it lies in quadrant 2. Its reference angle is formed by the terminal side, right here, and the x-axis. That is theta prime. Okay? So what we're saying is that this angle right here is called a reference angle. It is the distance to the x-axis from the terminal side of theta. And now this does depend very much on what quadrant you are in. So if you're in quadrant 1, the reference angle and the angle, it's the same thing because it's an acute angle. So basically, we only need to remember how to calculate reference angles for angles in quadrant 2, 3, or 4. The formulas vary because you're finding the distance to the x-axis. It's this distance here, that distance there, and this distance here. So if I want to know this one, I would take 180 degrees minus theta. If I wanted to know this angle right here, I would take theta minus 180 degrees. And if I want to know this angle right here, I would take 360 minus theta. Right, all the way around minus this theta would give you your angle. Okay, so when you look at the pictures, you kind of can see, okay, yeah, I see how that works. I take this whole angle here, right? That's theta. I take that minus 180 degrees minus this off, and here's what's left right there, right? That's my reference angle. So you really do need to know what quadrant you are in order to figure out a reference angle, and this works for degrees as well as radians. So you ask yourself, where is 345 degrees? Well, this is 360, this is 270, so 345 degrees is something like this. That would be the reference angle, okay? So I'm in the fourth quadrant. That means my formula is 360 minus theta. So it's 360 minus 345 degrees. So the reference angle here is 15 degrees. Not one of my common angles, okay? But still, I can still find the reference angle for this. Okay? The trick is knowing where 345 degrees is. The trick is knowing where 5 pi over 6 is. Well, 6 pi over 6 is 180 degrees. So 5 pi over 6 is right about there. Okay? That makes this the reference angle. So that means that my formula would be, since I'm in quadrant 2, it would be pi minus theta. Right? The formula said 180 degrees minus theta, right? 180 degrees pi, the same thing. If we're in radians, we're going to stay in radians. So I would do pi minus 5 pi over 6. And so my reference angle would be pi over 6. Okay? And we'll see what we're going to use this for in a few minutes. But now we have an angle, a positive angle, whoops, this one, a positive angle that's acute, that's in between 0 and 90 degrees. Let's try this one with negative. Negative 135 degrees. Again, the trick to doing these problems is to know where that is. Well, negative, so that means I'm going this way. All right, so that's 90, that's 180, so 135 degrees is something like that. Okay. Now, I'm in the third quadrant. The formula to find an angle in the third quadrant is theta minus 180 degrees. Or you can say, okay, if this is 135, you know, this is the reference angle right there. How much more to get to 180? And remember, I want this to be a positive angle, even though this is negative, okay? I want my answer to be a positive angle, okay? Because I want to figure out the positive acute angle. So I ask myself, well, okay, so if this was negative 135 and this is negative 180, what is the distance right there? And so theta prime would be 45 degrees. Okay? Because 1 negative 135 and another 45 would be 180. This is a little bit harder. Okay. 2.5. It does not say 2.5 degrees, so that means 2.5 radians. Well, this is pi over 2 radians. Pi over 2. That is the way we usually write it, but if we actually calculated it, it's 1.57. This is pi radians, which we should know is 3.14. Okay, well, what does that mean to us? That means that 2.5 radians is something like that. Okay. It also means that the formula for my reference angle, since I'm in the second quadrant again, is pi minus theta. 3.14 minus 2.5 to give me about 0.64. Okay. So, again, the hardest piece about finding reference angles is knowing what quadrant you are in. To find reference angles for angles that are bigger than 360 or less than negative 360, right, if we're going the other way, involves finding the coterminal angle. Okay, so we've seen that coterminal angles have the same initial and terminal sides, and that coterminal angles can be attained by adding or subtracting 360 or 2 pi, depending if you are dealing with degrees or radians. So our steps to find a reference angles for angles that are greater than 360 or less than negative 360, greater than 2 pi, less than negative 2 pi, find a positive angle less than 360 or 2 pi that is coterminal with the given angle, draw it in standard position, and then figure out the reference angle using the technique we just figured out, depending on what quadrant it is in. So, again, how do we do this? We just say, okay, 580 degrees, that's too big. Subtract 360, and we get 220. 220. Okay, that is an angle in between 0 and 360. Where is it? 220. All right, that's 90, that's 180, that's 270, 220, right there. Okay, so what do? Well, I take, to get theta prime, now I'm in the third quadrant, which means I take 220, the whole angle, subtract off 180, and I get 40 degrees. So my reference angle is 40 degrees. Okay. For this one, part B, 8 pi over 3. 8 pi over 3 is bigger than 2 pi, so subtract 2 pi, but we need common denominators to subtract fractions, which gives me 2 pi over 3. That is a number that is in between 0 and 2 pi, so that's good. Where is it? Well, that's pi over 2, right? 2 pi over 3 is, it was a little bit further, but that's fine, is right about there, which makes this distance right here, theta prime, is going to be equal to pi minus 2 pi over 3. Change pi to 3 pi over 3, and we get my reference angle is pi over 3. A positive angle between 0 and 2 pi, between 0 and 90 degrees, that is the distance from the x-axis to my terminal side of my angle. Last one. Negative 13 pi over 6. Okay, add to pi. Make this positive. So that's 12 pi over 6. So that is negative pi over 6. Well, I could kind of do it from here. I could add 2 pi again, which would give me 11 pi over 6. But let's think about negative pi over 6 for a minute. I kind of know where that is. It's right there. And if I want to know the reference angle, it's the distance from the x-axis to the angle. It's a positive distance. Reference angles are always positive. So this distance right here is simply pi over 6. 11 pi over 6 is all the way around there. And then I would take 2 pi minus 11 pi over 6, and I would get 1 pi over 6 as well. Okay, so we can use a little logic to help us out to find the reference angles. Reference angles always will be positive. There will always be an angle in between 0 and pi over 2, in between 0 and 90 degrees. Okay, so now that we have reference angles, what do we do with them? Okay, so the way that reference angles are defined makes them very useful in evaluating trigonometric functions. So the values of trig functions for a given angle theta are always the same as the values of the trigonometric functions of the reference angle, except the sign, plus or minus, not the sine function, right? The sign. So a function value of an acute reference angle theta prime is always positive. However, the same value for theta may be positive or negative. So what that means is if we take the idea of let's change this angle to its reference angle, then I can memorize all the trig functions, all the special angles in the first quadrant, and I don't have to worry about the rest of the unit circle if I just memorize the whole first quadrant. Because then I know that the trig functions of whatever angle I want are going to be the same as the reference angle, except if it's in the different quadrants, I know which ones are positive, right? If it winds up in the second quadrant, okay, the sine is going to be positive, the cosine is going to be negative. If it winds up in the third quadrant, sine is going to be negative, cosine is going to be negative, tangent is going to be positive, and so on. Okay? And that's pretty much what this is going to say. For example, we can use a reference angle of theta prime to obtain the exact value for the tangent of 120 degrees. So you know that 120, the reference angle is 60. We know the exact value for the tangent of 60 degrees is radical 3. We also know that 120 degrees is in the second quadrant, so the answer would be the negative tangent of 60. Okay? And the only way you know to put this negative is based on what happens in the second quadrant. Okay? So in the previous section, we used two right triangles to find the exact trigonometric values of 30, 45, and 60. And we're going to use the same idea for tangent 120, and we can find all the angles for which pi over 4 and pi over 3 are reference angles. Okay, so anything that has a reference angle, anything that's a quadrantal angle, or anything that has one of these three reference angles should be something that you can find the exact value without using a calculator of all 6 trigonometric functions for. Okay. So what do you do? How do you do it? Find the reference angle, theta prime, and then use the quadrant for which theta lies to put the right sign in front of it. So, sine of 135 degrees. Find the reference angle. First, where's 135? Well, 90, 180, so 135 is like that. So I know it's in quadrant 2. Okay, so now I find the reference angle. So in quadrant 2, I take 180 degrees minus 135 degrees, and I get that this angle right here, if this is 135, going all the way to 180, subtract it off, and we get 45 degrees. Okay, so now I need to have remembered what the sine of 45 degrees is actually equal to, right? It's part of our chart, it's part of the unit circle. If you haven't watched the video about something called the left-hand rule, you should watch that. Easy way to remember sines and cosines. And we get that this is the square root of 2 over 2. Again, there's no tricks to that. You can use a calculator. Some calculators will spit out this answer. Others will spit out 1.7, I believe that is. But that is something that you have to remember. You must remember the sine, cosine, and the tangent of anything with these 3 reference angles, 30, 45, or 60, and then their radian equivalent. Okay. So the sine of 45 is radical 2 over 2. Does that mean that the sine of 135 is radical 2 over 2? Well, also, think about this, that all students take calculus. We're in the second quadrant. The sign is positive. So yes, this is radical 2 over 2. Okay. These two are exactly the same. The number will always be the same. It just might be a minus in the front. Okay. Let's try one with a radian. Okay. Cosine of 4 pi over 3. Where is, come on. Where is 4 pi over 3? So let's think about it for a second. 3 over 3 is 1 pi, so that's there. So 4 pi over 3 is going to be right there. 4 pi over 3. Okay, now that makes this distance 4 pi over 3 minus. Okay, and that makes the reference angle pi over 3. So I'm looking for the cosine of pi over 3. The cosine of pi over 3, again, one of those that you have to remember, and it is 1/2. Okay, now I just must decide. Ooh, I'm down there. That means the cosine is going to be negative. So that means that the cosine of 4 pi over 3 is going to be negative 1/2 because I'm in the third quadrant. Okay? And that's all there is to it. Okay? So now, if I want to find something like this, the cotangent of negative pi over 3, again, I just decide what quadrant I'm in. Well, negative pi over 3, it's not going to get me all the way to 90 degrees, so it's going to be something like that, which makes its reference angle, cotangent, right? It makes its reference angle pi over 3, right? If we're going down pi over 3, right, the distance from here to here is simply pi over 3. Okay, so the cotangent of a positive pi over 3 is going to be radical 3 over 3. Again, something that you have to remember. And we can get that. Let's not jump right to that for a second. So the easier thing to do would be to find the tangent of pi over 3, which is definitely something you have to remember, which is radical 3. And that makes the cotangent at pi over 3 the reciprocal, which is radical 3 over 3. Okay, now we decide. Is it positive or negative? Tangent and cotangent go together, so they're only positive in these two quadrants. We are in quadrant 4, which makes the cotangent of negative pi over 3 in quadrant 4 negative radical 3 over 3. Okay. All right, so let's now use the same stuff, reference angles, to evaluate these trig functions that are now bigger than 2 pi or smaller or whatever. Okay, so the first one here is the tangent of 14 pi over 3. Well, let's just subtract 2 pi because that's bigger than 2 pi. So 14 pi over 3 minus 6 pi over 3 is going to be so that's still too big. So let's subtract 2 pi again. I'll just use 6 pi over 3, which is 2 pi over 3. So the tangent of 14 pi over 3 is exactly the same as the tangent of, I don't need parentheses there, of 2 pi over 3, because they start and stop in the same spot. 14 pi over 3 is just a little bit bigger. It's more spins around the circle, 2 more spins around the circle, in fact. Okay, so these two are going to be equal. Okay, now what quadrant are we in? That's 2 pi over 3, not quite 3 pi over 3. So we're in the second quadrant, and I know that the tangent in the second quadrant will be negative. Only the sine is positive in the second quadrant and the cosecant. But so now I just need to know the reference angle, which would be pi over 3. So the tangent of pi over 3, again, something that you should kind of know, is radical 3, which makes the tangent of 2 pi over 3 a negative radical 3. Okay? Because it's in the second quadrant. All right? Let's do this one. Weirder one. Secant. Okay, so first we're going to use the, well, first, I don't like that. I don't like a negative angle. I don't like that it's way too small. So let's change that. Let's say start at negative 17 pi over 4. Let's add 2 pi. Let's keep adding 2 pi. No, 8, sorry. 8 pi over 4. And when we add that, negative 17. We get negative 9 pi over 4, add it again, and we get negative pi over 4, add it again. Or you don't even have to, you kind of should know where that angle is. And we get a 7 pi over 4 angle, which means my angle 7 pi over 4 is right there, right? That's 4 pi over 4, 5, 6, 7, 8 pi over 4 is all the way around. My reference angle, again, which is why you could have stopped there, my reference angle is pi over 4, right? You could have stopped there, negative pi over 4. Reference angle for that is going to be positive pi over 4. So that means that the secant of 17 pi over 4 is going to be the same as the secant of 7 pi over 4, right? And it may or may not be the same as the secant of pi over 4, just depending on the sign, okay? So next, I don't memorize secants, but I know that the cosine of pi over 4 is equal to the square root of 2 over 2. And that it is positive in the fourth quadrant. So that means that the cosine of pi over 4 and the secant of pi over 4 are just reciprocals. The secant is going to be positive, so that makes the secant of pi over 4 the reciprocal of this, which is just the square root of 2. And so the answer to this question, the secant of negative 17 pi over 4 is going to be a positive number because it's in the fourth quadrant, so it is just the square root of 2. Okay. Whew. All right. These last 4 sections have had a lot, okay? Some of you might agree with the first line there. You feel a bit overwhelmed by the amount of information required to evaluate trigonometric functions. So you're right? Evaluating trig functions, like those in section 8, or the last example we just did, we're going to put a lot of stuff together. Okay? What do you really have to remember? Okay, so you do have to know the trig functions of my special angles. So we're going to be talking about this circle right there, especially these first 3 angles. You should know basically the degrees and radian measures in a positive direction of all these special angles in a triangle. We just talked about this, the signs of the trigonometric functions, right, that all students take calc. And that tells you what is positive in those different quadrants. And then the part that you have to memorize, right, is the, right, this table right here, the sine, the cosine, and the tangent of these 3 special angles. You can kind of figure out the quadrantal angles, right, just by making a point there, but these are good to remember as well. Again, and then using reference angles, you put a plus or a minus in here because the reference angle and the sine and the cosine are equal, except for the whether or not it's positive or negative. This is the most important thing right here. You need to remember the sine, cosine, or tangent of those 3 special reference angles. And know what we're talking about when we talk about the special angles on a circle. That's pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, and all the way around all these different angles, and this, of course, all the way around the circle is 2 pi. I wouldn't go crazy trying to memorize them in both directions, right? If you know where positive pi over 6 is, you should be able to figure out negative pi over 6 is just the other direction. So as long as you can remember the positive direction, that should be pretty good, okay? But there's a lot. There's a lot to calculating trig functions. There's a lot to using them uh, in different ways, and especially with it's easy to get confused with the values at the specific angles. Okay, but that is the end of 4.4 trigonometric functions of any angle.